This is a problem from your lab assignment, section 7.1. This is number 2. Now, we're going to do this a little bit differently. Instead of going through the process here and filling in the blanks, and then as we go along, let's see if we can go through this problem and solve it all the way through. So let's use integration by parts to solve this integral. This is e to the 3 theta times sine 4 theta d theta. All right, so integration by parts tells us that if we can identify a u and dv, then according to the formula for integration by parts, which came from the product rule, this is going to equal to u times v minus v du. So if we have u, we need to find du for the other side, and if we have dv, we need to find v by integrating. Okay. So let's see. According to what they wanted this setup, first of all, the u, if you had a choice for u's, usually polynomials and things that you cannot integrate would be candidates for u, and then the other one would be for v. But in this particular scenario, it turns out that it's not going to matter because both the exponential and the trig functions kind of alternate. The derivative and integrals of exponentials are exponentials themselves, and then the derivative integrals of sines and cosines are going to be cosines and sines. And so for this, it doesn't really matter which one you designate for u and dv, as long as you're consistent. So in this particular scenario, we're letting u, or they're telling us to let u equal a sine, the trig function, sine 4 theta, and dv is going to be equal to the exponential function e to the 3 theta. And there might be some times where we have to repeat this process, and we'll just stay consistent. We're going to continue to let u equal to the trig and our dv equal to the exponential. All right, let's go ahead and solve for this. Our u is equal to sine 4 theta, and so the derivative of that with a chain rule is 4, and the derivative of sine is cosine. So this is going to be cosine 4 theta. And then now the antiderivative, you would need to do a u substitution or a different variable substitution, like a t substitution. And then when you take a t substitution, the derivative of 3 theta is going to be 3 times d theta. And so to replace this d theta, you're going to have a 1/3 popping out. So let's put that 1/3 over here. And then the antiderivative of e to the 3 theta is just e to 3 theta. And then we don't do the plus c here because we're going to take the integral again and the plus c will come out. All right, according to integration by parts, our u as the sine 4 theta, our v, we just found that to be 1/3 times e to the 3 theta. And the same thing for our v here. And then our du, oops, let's not forget the d theta here. D theta. Our du would be this expression over here. So we have our d theta. All right. We can probably find ways to simplify things a little bit. So let's go ahead and do that in the next line. And we have a 1/3 over here that we can bring out to the front. And we have a 1/3 over here that we can also bring out to the front because it's constant. But then there's also this 4 that we can bring out to the front. So we get a 4/3. And now we have something here that's pretty similar to our original, except this one, our original problem had a sine, this one has a cosine. So what we're going to do is we're going to take this expression and perform integration by parts. So let's copy this business over here, And remember that we're going to want to work with this. So we're going to find a replacement for this. We're going to compute this integral right here. So let's do that. In between these lines. Okay, so we're going to do another u substitution or integration by parts. Now remember that the original u and dv designation was that we let the u equal to the trig and then the dv equal to the exponential. So this is our problem. We're going to let u equal to our trig and our dv equal to our exponential. All right. So the derivative of this, the derivative of cosine 4u is going to be 4 times sine, oops, for theta. But it's a negative, so we have to keep that in mind. We have a negative sine 4 theta times 4, the derivative of the inside. So that's our derivative of, for u, that's what du is equal to. And our dv is our exponential, so we're going to get the same result as we got up above. So that's why I just kind of quickly copied and pasted that. So now this thing, according to integration by parts, is going to be equal to uv minus the integral of v du. All right, so let's figure out what these parts are. U is this. Whoops. All right, so that's u, and then v is this minus v again, and du, this time it's equal to this thing. So let's be careful because we have a negative popping up. This is actually multiplying. So this is our v du. Let's put this in a slightly bigger integral here. There we go. Okay, let's see if we can simplify this. We're gonna again get a 1/3 out of this thing. So let me copy. This is how I simplify things in my computer. The 1/3 can come out. And so we have the exponential and the cosine function here. Now there's this 1/3 that can also come out, and then this -4 can also come out. And so the negative and the negative will become a positive. And then we have a 4/3 here, and then we have this thing. Now if you look at this carefully, you should see that it looks familiar. We'll come to that in a minute. But now we have a simplified version of e to the 3x times cosine 4x dx, or e to the 3 theta times cosine 4 theta d theta, and that's equal to this whole thing. Now we have another trig and exponential function in the integral, but like I said, this should look a little bit familiar, and we're going to try to figure out what that is. Okay, so back to our problem. This is our original problem. You should see that it kind of looks like our original problem. And we wanted to replace this. Okay, so this is what we got. So I'm going to copy this whole thing and replace it here. All right, what do we have? Our original problem, e to the 3 theta is equal to, or the integral of e to the 3 theta times sine 4 theta d theta has so far been equal to this 1/3 and then sine 4 theta e to the 3 theta minus 4/3 times, now this latest integral that we just found is here. So what we can do is we can distribute and multiply things out. So let's see how we can do that. We have, so let's first of all copy what we have, and then now this business over here is going to be 4/9 with a negative sign, minus 4/9. And then we have this expression over here, which is that exponential and the trig function. And then we have a minus and a plus, so that's going to end up to be a negative. And then we have a 4/3 and a 4/3. I think that's 16/9 times this integral over here. All right, so that's a little confusing, but let's take a look at this. Let's actually make this screen a little bit bigger so we can see a slightly bigger picture of this. I want to take this expression and what this is equal to. So let me do that by quickly doing a copy and paste. And let me take this middle part out. And maybe if I shrink this a little bit, we can see a bigger picture. All right. So what do we see here? We see this integral is equal to this expression with the exact same integral on the other side. Now this is almost like saying this whole thing, if we let this whole thing equal to x, we have this expression and then we have this x over here. Well, you're really solving for this value over here, which is x. And so what we can do is we can add the 16/9 times x on both sides. So why don't we do that? Let's take this, add this to both sides. And then we have this thing, 16/9, with a common denominator of 9. 9 plus 16 is 25, so this is going to be 25/9. And times x, but x is equal to this thing, if you remember. So let's replace that back with x. And so now if we want to solve for this, we want to get this by itself, we'll just divide out by 25/9. So what are we going to get? we're going to get 9 over 25 times this whole thing. So let's put a big bracket around this and multiply this by 9 over 25. Okay, so that's it. This is your solution all by itself. All right, that was a lot of work, but let's see if we can walk through the process here and see if we can answer what it is they're looking for. Okay, so this is one of these integration by parts where you have to do a roundabout because the exponential and the trig function have derivatives that are equal to themselves. After a couple of integration by parts, you'll see your original integral on the other side. All right, let's walk through this. We have some of the answers already here. So if u is equal to the sine of 4 theta, then du is going to equal to positive cosine of 4 theta. D theta. Oops, the d theta is already here. And then the integral here is going to be the 1/3 and then e to the 3 theta. Okay, and we won't do the plus c here because, oops, the plus c, speaking of the plus c, let's just throw this at the end, and that's usually good enough. All right. Oh, we forgot our 4 here. Because of the chain rule, the derivative of sine 4 theta is going to be cosine 4 theta times 4. All right, according to integration by parts, the first part is going to be u times v, so it's going to be sine 4 theta times e to the 3 theta divided by 3 minus the integral of v du. So v and du, so v is e to the 3 theta, which is already here, and du has a cosine theta, so there are constants that we can add on. So there's a 4 in the numerator and then a 3 in the denominator. Okay, so far, if you're following along, we've gotten through this portion right here. Okay, so now the next step is that we have this integral, and we're going to apply integration by parts here as well. So we're going to let u equal to the trig again, and the dv equal to that. So the derivative of the trig is, remember there was a negative because the derivative of cosine is negative sine, and then the chain rule gives us another 4. And then our antiderivative was the same, 1/3 e to the 3 theta. And now uv, so u was cosine, v was e to the 3t. So we have cosine 4 theta times 1/3. Okay, so e to the 3 theta. And then now we have constants. Now there's a negative here, but there's a negative here as well, so this is going to be negative 4, and then the denominator for the 1/3 e to the 3 theta is 3. Okay, so we found this integral right here. We found this integral, and then we got it to be this, and now we're going to replace that integral back All right, let's see how they do it here. So this is the original problem is once again present. In fact, putting it all together, the integral, if the integral is equal to this, then we have the integral is equal to this part that we got, and then 4/3 times 1/3 times 4/3 the integral, and there's that c that pops up. So this is essentially this business over here, the 1/3 e to the 3 theta cosine 4 theta plus 4/3 times the integral, the original integral that we got. So that's what we're looking at here. So this could be rearranged by solving for I. So actually I is still here. So what they're gonna do is distribute just like we did. We have 4/3 times 1/3, that's 4/9, minus, so this negative 4/3 times positive 4/3, and this is where they got the 16/9 times the integral. And now we're going to solve for that integral, bringing the integral on the other side. So they had I, we used x, so we bring the integral over to the other side, we're going to get 25/9 times that big mess. And so if we're going to divide that through, the integral is going to equal to 9/25 times that big mess. So I wonder if they want us to type everything in. We solve for I. Yep, looks like we're going to have to type everything in. So we have 9/25 times the rest of the thing in brackets. So what's going to go in the brackets? We have the 1/3 e to the 3 theta times sine 4 theta minus 4/9 e to the 3 theta times, this time with a cosine 4 theta. And then the C1 also gets multiplied by 9/25, which is equal to this. Okay, so I think this is the same thing. So let's just copy and paste that and see what they say. Oh, we forgot our capital C, our constant. So let's do a plus C, and then we're good. Okay, so I hope that helps. That took a little while, but I think that whole process is good to know for these types of integrals. Okay, good luck.